now, virtually programming. VirtuallyProgramming.com.
So finally we're ready to texture our model here and make it look a little bit better. If we run this, just get a kind of a preview of what it's going to look like. You can see Professor Zombie in all his glory here. He's no longer flat shaded, he's garage shaded, so you have a much smoother look. It's not all faceted and flat. Although if you look closely you can kind of see the edges of the triangles, which is kind of a giveaway that it's kind of an optical illusion, the smooth shading. But anyway, you can see the specular highlight off his chest. That's using the blend shader. He looks kind of glossy because of that blend specular highlight. And again, we can set that specular amount. I think we decided 45 looked pretty good. Yeah, you can really kind of see that specular dot, but it also makes those edges kind of really sharp so that you kind of see the triangles in the model. Kind of see the light off his boots a little bit. Some of the normals in the model are probably not correct. In fact, right there above the ears, there's something weird going on there. And I don't know, that's probably, if that's a problem, if assuming that can be fixed, it probably needs to be fixed in the modeling program. That's probably a problem with the model itself, really. But you can kind of see those blend specular highlights reflecting off of the model. You also, in his collar there, you can kind of see some gaps. That's a problem with the model. Depending on how closely this model is going to be looked at in the game, you might want to fix that, or you might not. To fix it, you basically have to put a surface in there that can be seen, because what's happening is, since you can't see the backside of the triangles, it doesn't draw, and the inside of the jacket is the backside of the triangle, so the inside of the jacket won't draw. It's just the outside, and so once you look inside the jacket, you can really see holes. Anyway, so let's look at the code here for texturing. This is almost identical to what we've just been looking at in the blend shader. The differences are, we're actually going to use this color map here. This is our texture. It's the picture file that we're using as a texture. And then, of course, in the input, we're passing in the UV coordinates, which are the texture coordinates that map the points in the picture to the triangle that is texturing. We've been passing that for a while, I think, but we're going to use it now. And then the sampler is very new. The sampler samples colors out of the texture, and it basically determines how the texture is going to get drawn across the face of the triangle. And so here we're saying that, let's see, the texture that the sampler is going to use is the color map texture. And for minification and magnification, we're using linear. I'm not sure that this tutorial is really the place to get into minification and magnification, but the short version of that is that the texels in the image, if you think you've got your texture image, the pixel elements within that texture are called texels, because they're not necessarily drawn on the screen. They don't become pixels until they're actually drawn on the screen. So the texels within that image are not necessarily the same size as the pixels on the screen. Depending on how close the image is to the camera, it might be very far away, and so the texels are drawn very small compared to a single pixel, or it might be super close, and the one texel covers 50 pixels or something like that. So minification and magnification have to do with how that is handled, how you translate those texels into pixels when the sizes are not one for one, when one's bigger than the other. Forget which one's minification, which one's magnification. I think when don't get me to line. One's one direction, the other's the other direction, and you can kind of set in the sampler here how to handle those calculations, and it'll affect the look a little bit. I think where I've seen it make a difference is like when you're looking at like a wall or something and you're looking at it at kind of a steep angle. It can affect how it looks, how it draws, and you may want to play with those settings a little bit, but that's really probably a little bit beyond the scope of what I want to cover today. Once you start texturing things and playing around with this a little bit, you can kind of research samplers a little bit more and kind of get into the specifics of what all these things do. Now, the address U and address V clamped is probably what you're going to always want to use with models and texturing. This is your UV coordinates in your picture, in your texture, and this setting is going to determine what happens if you go out of bounds. So if you imagine your texture, the upper left corner is 0, 0, the bottom right corner is 1, 1. What if you set the value to 2, 1? You're out of bounds. And so what does that actually mean? And the clamp, I think, is basically saying if you go out of bounds, we're going to keep you in bounds. You go to 2, 1, we're going to change it to 1, 1, and or some interpolated value between that or something. But it's going to limit you to where you cannot go outside of the bounds of the texture. And there's some mirroring options or wrapping options where the texture will just kind of repeat if you go out of bounds, or it'll repeat in a reverse fashion so it's mirrored. For texturing a model, off the top of my head, I can't think of a situation where you wouldn't want it clamped. If you're repeating a texture across a surface, like with a terrain, you're not going to be using a model. You're going to be probably defining that with an algorithm and building your own vertex buffer rather than using a model. But there you probably want to repeat the texture across the surface, and you would use this address U and V to repeat the texture across the surface multiple times. Let's see, so let's look at the technique is actually the same. So the data type here is sampler 2D. This is going to sample a 2D texture, and we're setting the sampler state here, and this is the name of our texture sampler. The vertex shader input, I think, is identical to what we had before, and I believe the vertex shader output is identical. We have the blend specular highlight, the blend shader here, that we just looked at, and I don't know if I may have forgotten to mention that blend and Phong are generally, you actually hear it called blend Phong rather than blend or Phong. And I think that blend is considered blend Phong. Phong wouldn't really be considered blend Phong, but I think the reason they call it blend Phong is because it's blend's algorithm, but blend basically just kind of figured out a different way to do Phong's algorithm. So it's really Phong's, but blend changed it, and so it's called blend Phong when it's blend. So that's what we're using here, and we've covered all that. The vertex shader is exactly the same, except that UV value actually has a value in it. Up to this point, it was empty and it was passing nothing on, but it's still the same code. We're taking that UV value passed in with the vertex, passing it out to the rasterizer, which is going to send every pixel across the face of that triangle to the pixel shader, and the UV is going to be part of that. But like with pretty much everything else, the UV values are going to be interpolated across the surface. So it will send a UV value for that pixel, not for that vertex. So every pixel will have its own unique UV value and will map to the correct spot within the texture image. For the most part, we have the same thing here. I think that texel value is new. We'll cover it when we get to it. Going through all this, I think all of this code here is exactly the same as it was in Blend. The difference, the new thing here, is this texel value. We're using the text2d function to use our sampler to map the UV coordinate of this pixel on the triangle surface to our texture. And so we're using this sampler to determine the texture, and this sampler uses our color map texture to pull colors from. So it's looking into our texture image and mapping a UV coordinate on the surface of the triangle to a texel within the image, which is returned here, which is the color of that texel, which will eventually be a pixel color. And we set the alpha to 1 just in case it's messed up for some reason. I doubt that's actually necessary. Let's try commenting it out. Yeah, that looks fine to me. I don't see a problem. Not sure if there might be a condition where that's actually needed. Sometimes I forget why I put this stuff in here, and I mostly learned how to do this and compiled all this out of other people's examples, and so sometimes you hang on to something that was in somebody else's example and then forget why it was done, especially if you don't know what you're doing and why you're doing it. Hopefully I kind of sort of understand what I'm doing here since I'm explaining it, but yeah, I'm not sure why I included that. I think it's going to be 1 anyway, and resetting it to 1 is not going to change it. And then here's how I combined the the colors. I'm basically multiplying the diffuse light color with the texture image and the ambient light color with the texture image. Otherwise, the backside would be black. See, you can look at his pants. You can see the backside of the pants. If I did probably, let's see, not that, do that. If I take that texture out of there, I bet you it's going to be black. Yeah, it's a silhouette. It's gray, but it's still a silhouette. And interestingly, it affects the front side too, because the ambient light gets applied to everything. It gets applied to the front side and the back side. So it kind of messed that up as well. So we're just combining that texel value with the ambient light color and adding that to whatever diffuse light and texel color there is, and then adding in our specular highlight where it applies. And that's basically texturing. You know, it's like once we get past the Phong shader, it starts going pretty fast. That's really as far as we're going to go with it for this series. Normal mapping would bring in another texture, and the texels in the normal map would be used to determine the vertex normal, or just the normal. It would be used to determine the pixel normal. Every pixel on the face of the triangle, instead of calculating the normal, it would pull it from the normal map as a texture and use that normal to determine what direction the pixel faces, which gives you a lot more control over what direction every pixel faces. In this case, we're interpolating across the face of the triangle between the corners to determine what direction it faces. And so all we can get is the Gerard smooth shading. But if we use a normal map, we can define the direction that every single pixel faces on that model and make them point in, should I say, odd directions, which can, instead of making the surface look smooth, can make it look rough. And before it was flat, then we went to curved and smooth. Now with a normal map, you can not make it smooth, but you can rough up that rounded edge or that rounded surface and make it appear to have texture to it. Anyway, we're not going to cover that here. I'm probably going to wait a while before I get into normal mapping. I've got to make some demo stuff and whatnot, but eventually I'll do something to demonstrate normal mapping, but it's probably going to be deeper on the DirectX side.